right, so welcome back. We'll be continuing where we left off last time with variables. A couple of things to remember is that there's no class on Monday, and consequently there's also no help hours or office hours on Monday. So make sure that you're making full use of Campus Wire to ask any questions online if you're needing help with that first hack or those readings. We left off talking about variables because, of course, in our program over here, miles to kilometers, we kind of said, well, we've got these variables called miles and kilometers, and we use them down here to compute how many kilometers there are in the number of miles that you give. So we need to talk about that in a little bit more detail now, other than what we did on Wednesday. Let's see. So first of all, we looked at we're going to focus our attention only on three basic types of variables: integers, which are whole numbers; doubles, which are floating point numbers and can represent fractional values; and characters, which come from that ASCII text table that you can check out online there. We said that C is a statically typed language, and what that means is that you have to declare your variables and their type before you actually use them, right? That statically typed simply means that you have to declare them and then you can use them afterwards. Let me go ahead and show you the consequence of not doing it in the correct order, right? What if I wanted, and here's a preview of how you can set a variable. What if I set miles to 10.5 instead up here? Now let me go ahead and try to compile this program. It's not going to work because it has no idea what miles is. It's undeclared, right? Because you have to declare it before you can use it. I can't use it on line 14 when it's being declared on line 16. A variable scope is the area of code in which it lives. The scope of a variable is the section of code in which it can be seen, right? In other words, it exists. Right? It does not exist on line 14, and consequently the compiler is going to complain about that. It does, however, exist on line 16, and it exists all the way until the end of our program. Remember that the code block opens with a curly bracket, closes with a curly bracket down here, and so when we declare this variable on line 16, that's where it's born. It lives its life out until line 28, at which point the block of code ends and the variable is out of scope. Right? We call it scope because imagine that you're looking at a binoculars or the scope of a submarine or something. You can't see everything. You can't see all the variables. You can only see what you're focusing in on at the time. So you have to declare them in the proper scope and in the proper order. Now when I compile this, it's going to compile just fine, because down here, when we actually use the variables to read in miles and use miles and print out miles, then it exists because we successfully declared it up here. That's all that statically typed means. And that it means that it has a name. We'll talk about names here in a moment, though. But there are limitations, okay? For example, an integer, an int, is a 32-bit assigned 2's complement integer. Now don't worry about that technical babble, whatever. You're going to learn about that in, say, a lower level systems level course where you look at how these things are actually represented. For now, however, you can the takeaway here is that you have a limitation on how big it can be, right? It can be as big as, or as small as, negative 2.147 billion and change, and as big as 2.147 billion and change positive. Right? It can represent 0 and negative numbers in that range and positive numbers up to that range. And these numbers are derived from base 2. Right? So bits are zeros and ones. They can only represent two options. It's not like our counting system that goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Computers don't have 10 fingers and toes. We could build computers like that, but they're going to be very, very error prone. Instead, 0 and 1 turns out to be the best way. Positive charge, low charge, high charge, no charge, right? On, off. Computers and equipment like computers are extremely adept at discerning between those two different states. They're not going to be as adept at discerning between 10 different states, and that's why all computers are binary. So why can we represent negative 2.147 billion and change? It's because we have 32 bits. One of them is used for the sign, negative or positive over here. That means that the remaining 32 bits can be used to describe the actual number. And if I gave you, say, 4 digits, you could represent 0 up to 9,999, right? Well, this is not base 10, right? I'm only giving you bits. They used to be called bidgets, right? Like digits. So you can represent 2 up to the power of 31. And that's where this number comes from. 2 up to the power of 31, but minus 1, why? Well, we have to start at 0. So if we start our counting at 0, 1, 2, 3, 4, all the way up to 2 to the 31st, we can't go any further than that. Let me show you what happens if you try to exceed this. So I'm going to go over here to my demo code instead. And instead of printing out hello world, let's go ahead and create an integer, x, and set it equal to that value right there. We're going to print it out. X is equal to %d and the line. We'll talk about printing here hopefully by the end of the day. And let's print this out. Everything is going to be perfectly fine here. I'm going to go ahead and compile this demo and run it. I can represent 2.147,483,646. What happens if I try to add 1 to it? And this is a preview of what we're going to do here in a second with addition. I'm going to try to add 1 to it. Right? So that is more than we can actually represent. Something that's going to happen here is what's called overflow. Right? Oops, let me recompile it and run it. So normally this would be 2.147 billion blah, 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 648. But what happens is it wraps around to the negative value. Because unlike real numbers, if you look at the Cartesian plane, right, you've got x and y axis. X and y, they go off to infinity, negative infinity, positive infinity, right? It goes on forever. Computers are not infinite machines. They're finite. So their number line doesn't look like this. Instead, it looks like a circle. And if you go too far in one direction, then what happens? You wrap around back to the negative. So if I go positive, positive, positive up to 2.147 billion and change 647, what's going to happen? I'm going to jump right around to the negative values, and that gives me this negative value over here. That's called overflow. Right? So exceeding the maximum or minimum values, you can go the other way as well. It's called underflow. Right? So if I started at 2.147 billion, blah, 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 648, and I subtracted one more, what would happen? I would end up back on the positive side at a very, very large number. Right? So those are some limitations of integers. And you might be asking yourself, well, that's pretty small, right? That's not big data. We live in the world of big data now. And yes, there are libraries that let you do larger numbers. Arbitrary precision numbers, but they're going to be way slower because you're doing everything in software then instead of hardware. A double also has its limitations. It's a decimal number that only has about 16 to 17 digits of accuracy. The representation here, it's an IEEE 754 floating point number. Again, you'll deal with that when you get into systems level programming. Just know that you only have about 16 digits of accuracy, 16, 17 digits of accuracy. Because you're only working with 64 bits. In fact, that's why it's called double, right? You have double the amount of 32. You have 64 bits to play around with. So for example, we could represent, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's way more than 17 digits already, right? So let's go ahead and change this to a double. And let's try to print this out now. And let's go ahead and get rid of this stuff. Is it going to preserve all of my numbers? Nope. All right, in fact, the printing here is we'll talk about printing here in a second, but let me print out 40 digits here. Let's go ahead and GCC this, a dot out. Oops, come on, save it. There we go. There we go. So is that the number that I wrote down? 10, 11, 12. Ooh, what happened there at 13? I did that number so that it was very predictable. Did I get 10, 11, 12, 13? Nope. Why? Because I only have about 16, 17 digits of accuracy. At some point, you're going to start losing that accuracy. Here's another example. Instead of printing out X, let's print out something that we do recognize here. Oops, sorry, it's M underscore pi. And if I'm going to be using pi, what library do I need to bring in from that we briefly talked about on Wednesday? the math library. So include the math library .h. There we go. And let's go ahead and print out pi, but we'll print it out to 40 decimal places. Is that going to work? Well, I have no idea. 1415926 something something something. Is there a Wolfram Alpha canonical definition of pi? Pi. All right, there it is. I have no idea, but let's go ahead and compare those two numbers. Pi is actually this. So 1415926535897, and then there. That's the digit at which it starts to diverge from the actual number. Why? Again, computers are finite machines. They don't have an infinite amount of memory to be able to hold an infinite number of digits of pi. Instead, you're only going to get about that much accuracy. Right? So there are limitations to both of these things. Okay. What about naming conventions? Naming variables. Right? So names cannot have spaces, should not have other weird characters. Right? No Unicode. Like I did on Wednesday, I copied the smiley emoji and put that in as my variable name. Don't do that. No Unicode, no hyphens, etc. Right? They cannot begin with a number and should not have any numbers. Right? In other words, don't name your variables variable 1, variable 2, variable 3. Those are terrible variable names, right? Terrible variable names. Variable names. Like, or here, let's go with code mode here. X, Y, A, B, variable 1, variable 2, right? Foo, bar, baz. Those will be common placeholders that you see all over the place. But though, if you're actually programming something, you need to be descriptive. Best practice, be descriptive. Your variable name should represent what it represents. So for example, a great variable name would be number of students. I think we're at 81 in this course right now. I could set that, I could create a variable name called number of students. Sometimes, say, X and A may be okay variable names. Right? You do this all the time in mathematics, right? X and Y, because that's associated with the Cartesian products, the x-axis and the y-axis. And why are they doing it that way? Well, because mathematics is abstract. What does X represent? I don't know. I don't care. I'm just doing math, right? When you actually say that, well, X represents time, call it seconds, right? Or X represents, dollars, call it dollars, or whatever those dollars are representing. So number of students is a much better variable name, right? Avoid abbreviations. Ambiguous, I should say. Ambiguous abbreviations, right? Social Security number, SSN, may be okay, but say, I don't know, something arcane. EIDR, like we talked about, EIDR, excuse me, is not, right? That's very niche, right? Unless you knew that was like an ISBN for a book, and even ISBN, International Standard Book Identification Number. I don't even know what it stands for, but that's how you identify books. EIDRs are how you identify movies, etc. Right? So avoid ambiguous abbreviations. Sometimes it's okay, sometimes it's not. Use a consistent naming convention. Right? So, for example, our recommendation is to use lower camel casing for variables. Right, this is a modern convention. Right. Note why do I call it lower camel casing? Well, if it's a compound word, multiple words, the first word is lowercase. Each subsequent word, the first letter is uppercase. And it makes it really easy to read, right? If you didn't do something like that, if you had lower camel casing, right, that's really, really difficult to read because you don't know where one word begins and another word ends. However, if you use lower camel casing and capitalize each letter afterwards, then it's much easier to read, right? Another option would be old school. C would be a lower underscore convention casing. Right? Now here, what I've done is instead of uppercasing the first letter of each subsequent word, I've put an underscore between each. Why? Because you can't have white space. White space means that it's a new word, right? So underscore here keeps all those things together without having to use white space. The disadvantage here is that what are you always doing? Between each word, you are putting your pinky on the shift button, going all the way across the keyboard and hitting that hyphen to get that underscore. You are going to kill your pinky really, really quickly if you follow that old school convention. So my recommendation is to use lower camel casing for your variable names. You can also do upper camel casing. This is, say, in other languages, Java, etc., right? It's not so common here in C, but later on, we'll use these for enums, numerations, and structures, right? But that's much later, so don't worry about that. You also have upper underscore casing, right? And we've already seen this, right? When I printed out pi, what did the math library choose to name it? M underscore pi. M to emphasize that it's in the math library, and then all uppercase pi, and separated by that underscore there. So this is usually used for constants, or macros, right? So if you want to create a constant that nobody changes, right, you can say this is a constant, and you can trust that nobody's going to change this by using upper underscore casing. That is a convention used, right? So basically the takeaway here is be consistent. That's what we're going to be grading on. Don't use underscore casing on one variable and then lower camel casing on the same variable and a different variable in the program, because that's not consistent. Follow a consistent naming convention and you'll be okay. Right? Variables should be descriptive, but also variables should be nouns because they are people, places, or things. Later on, when we get into functions, functions do things. Functions will be named verbs, right? Because again, we want our code to look as English as possible, to look as natural language as possible, even though it's not possible, right? Okay, so those are variables. Well, once you've got variables, you need to do something with them. So let's talk about operators. Operators. I spelled that correct? Yep, good. All right. So operators. Where are we? All right. Well, the first operator that you need a way to get values into variables. So, for example, we use what's called the assignment operator to do that. And I did that already a couple of times here, where I set x equal to this number. Over here in miles to kilometers, I set KMS equal to this expression on the other side, right? To do this, you use a single equal sign, okay? That's the syntax. It's a single, let me emphasize that, single equals sign. Right? Why is it like this? That's not algebra. Well, this isn't algebra. If you were to look at this from the perspective of algebra, you'd say, oh, the thing on the left-hand side is equal to the thing on the right-hand side. And either that's true or false. Maybe it's true, maybe it's false, right? A plus 5 is equal to 4y, right? That's an algebraic expression. This ain't algebra. This is programming. So what it means is it means to take the thing on the right-hand side and to put it into the variable on the left-hand side. There we go. Right? It's not an equals as in algebra. It means take the value on the left-hand side, LHS, and place it into the variable on the right-hand side. If you try to do something wonky, say like putting, I don't know, x plus 5 is equal to 4 minus x, right? That is not going to compile at all. That seems like an algebraic expression, but the thing on the left-hand side is not a variable. The thing on the left-hand side is an expression, x plus 5. That's not going to work. The thing on the left-hand side has to be a variable. If it's just a number, it's also not going to work because it's got to be a variable on the left-hand side. So the left-hand side has to be a single variable that you assign. Now, technically, there are languages, I think C might be one of them, where you can provide a list of variables. We're not going to get into that weird syntax, though. Okay? All right. The right-hand side can be a scalar that is just a single hard-coded value, say like a is equal to 5, right? It can be an expression. Right? Say that a is equal to 5 times b, right? Or something like that. We'll get into the other operators here in a second, okay? It can be a complex expression, So for example, if I want, I'll save that for in a second here, but think about the quadratic equation, the quadratic formula. How are we going to be able to write that? Well, it's very, very complex, right? It's got a numerator and a denominator, and it's got a square root and all that kind of stuff. So we're going to have to, by the end of the day, we're going to be able to get there. But otherwise, you've got algebraic operators, arithmetic operators is what I should call them, arithmetic operators. Right? So here we go. We've got plus, which is addition. We've got minus, hyphen, which is subtraction. We've got multiplication. It is not x. It is not that c dot, and it is not just a blank space there. Right? Like you can say A, B, that math would allow you to do that, but code doesn't allow you to do that. The reason that it's not these things is because the QWERTY keyboard was made and established like 100 years before modern computing with typewriters. I don't know if the exact year that it was made, but look in your keyboard and search for those symbols right there for multiplication or even for division or this fraction right here, right? You don't see anything on your QWERTY keyboard to support those. So what is the closest thing? The closest thing is going to be the asterisk. What is the closest thing for division? It's not going to be that quotient or whatever they call that symbol there. It's going to be a forward slash or backslash there. Forward slash. Right? Those are your arithmetic operators. Right? And then finally, you also have PEMDAS rules apply. Right? Remind me, what is PEMDAS? Yeah, PEMDAS is equal to parentheses, exponents, multiplication, addition, subtraction. There's an order of operations. The following are not equivalent. Right? If I go A times B plus C, which one of those things is going to get evaluated first? A times B and then the addition versus what if I wanted the addition to be first? I need to put it into parentheses. You can add as many parentheses as you want or as needed to make sure that your things are valid, that your expressions are valid. Now we have enough to actually do this quadratic equation here. Right? So x is equal to negative b plus minus square root of b squared minus 4ac all over 2a. Well, first of all, this is not even really math. This is just shorthand for two equations, a positive radical and a negative radical. So let me come over here and let's go ahead and get rid of some of this stuff. Let's go ahead and double A, B, and C, right? And I'll say double x and double x. 1 and 2 here, I'm violating my naming rules already, but what does x stand for? I have no idea, right? What is the x-axis standing for here? It's too abstract, so I'll just go ahead and use x1 and x2. Right? So how do I translate this value here to code? Well, first of all, I need a negative b, right? Well, how do I get a negative? Same way you would do in math, minus b. Now, plus or negative b minus, right? Those are going to have to be separated. Now, how do I get that square root? I'm going to call in the math library here and the square root function. Square root, b squared. So some of you might be tempted to use that. That will compile and work, or that will compile and do something, but it won't be exponent. It won't be squared. This is actually a bitwise exclusive OR operator. All right? So how do I do b squared? Yeah, just cut that Gordian knot. All right? B squared is what? B times b. That'd be the easiest way. I do want to make you aware, though, that if you need to do this with arbitrary values, say like b to the 1.5 or something, right? Then what you can do is use a POW function. POW is short for power. I will raise b to the second power there. Right? Again, you can do arbitrary values, x to the y for any x and y. Right? What happens for 0 to the 0? Hold that thought for a second. Right? All right, so then b squared minus 4ac minus 4ac. Is that correct? It's very, very mathy, but is that Cody? No. Nope. You can't do that. Oh, okay, x. X is multiplication, right? No. What's multiplication? Asterisk. Asterisk, asterisk. There we go. And then all over 2a, or 2 times a. There we go. Is that correct math? PEMDAS, left to right, right? What's going to happen here? With the numerator, I should say. Is this all one expression right now? Not as I've written it. What is it actually going to be divided here? This thing right here. So if I want all of this on top, I need to write more parentheses. PEMDAS. Remember the P in PEMDAS. Parentheses. Let's go ahead and repeat that, but for minus and then x2. There. That should work. Right. I'll go ahead and put that in the notes for your translation. Right. All right, so there are some pitfalls here. Let me get rid of this. There we go. Pitfalls. Right. So truncation. When you add, subtract, or multiply two integers, the result is always an integer. 2 times 5, 5 times 17. You are always going to get an integer out of that. Plus, minus, likewise. However, in code, division of two integers is also always an integer. All right? What do I mean by that? Let's go ahead and take a look at an example. Let's go ahead and create a couple of integers here. Int a is equal to 10. Int b is equal to 20. Let's go ahead and create a double here. C is equal to a divided by b. And let's go ahead and get rid of those 40 there, %f. And c, let's print that out. And we don't need to know pi anymore. I'll go ahead and get rid of that as well. Right. Now, predict. Well, first of all, in the math world, if we go over to the math department and ask them the really hard question of what's 10 divided by 20, what will they answer? 0.5. But in the code world, it ain't. Right? What happens here is that 10 is an integer, 20 is an integer. So 10 divided by 20 is an integer. Well, is 0.5 an integer? Nope. So what happens is that 0.5 gets cut off and thrown away. It's not rounded down, it's not rounded up, it's just the fractional value is just simply thrown away. Right? And that's what happens. That's called truncation. When two integers are divided, the fractional part is thrown away. Right? This is truncation. Okay? So you do have to be careful about this. 20 divided by, or let's say 10 divided by 20, because that's what we are doing, should be 0.5, but it ends up as 0.0, right? Because of that. You just end up with 0. To solve this, you can use typecasting. Right? So let me come back over here and try to fix this. What I'm going to do is I'm going to add a double in parentheses in front of one of the variables. What that does is it says, for the purpose of this division, for the purpose of a divided by b, temporarily treat b like a double. Now a double divided by an integer or an integer divided by a double will be a double. That 0.5 is going to be preserved. Right? Let me go ahead and show you. That 0.5 is now, value is now there, right? Because we did this typecasting here. So I'll make sure that you have this in the notes so that you can see it. But otherwise, you might be asking yourself, well, wait a second, if this screwy thing happens, and by the way, it happens in every single statically typed language. C#, Java, C, C++, Objective-C, Swift. I can think, the only ones that it doesn't happen in are dynamically typed languages like Python, JavaScript, PHP, right? Where things can change willy-nilly, right? And it really, believe me, it's not that great. Those languages aren't that great with respect to that feature. But you might be asking yourself, well, why do we even bother with integers then? Why don't we just make everything a double? After all, 10.0 or 10 can be 10.0, right? I could just make this into 0.0 and 0.0 and make this into double, make this into a double, and make this into a double. Why do I ever need to worry about integers at all? It's because integers are exact. Over in the math department, if you were to ask them, what's 1/3 plus 1/3 plus 1/3? They would sanely answer you what? 1. That's not how it works in a computer. 1/3, remember, it's finite. 1/3 is 0.333333. At some point, you run out of digits, right? And then 0 after that. So what is 0.33333 plus 0.3333 plus 0.3333? It's 0.99999, not 1, right? So you do need, when you need precision, when you need preciseness, you do still need integers, right? You can't get away from them. But otherwise, you can use typecasting here to solve this problem. And there we go, all right? PEMDAS rules, some other pitfalls. Sometimes you do invalid operations. For example, what if I did, say, 1 divided by 0? Or what if I did, I don't know, square root of -1? Well, in mathematics, what's square root of -1? I, right? An imaginary number. In mathematics, what is 1 divided by 0? Undefined, right? What happens when you take a calc class, though, and you realize, oh, wait a second, we can take a limit as we approach 0? What happens? The number gets bigger and bigger and bigger. It becomes infinity. What happens if you try to do, now let's do that power. Pow, I'm interested to see what that does too. What is 0 to the 0? That's also undefined, right? Although you'll get people who don't know any better trying to argue against that. Double x is equal to, let's try all of those things. Let's try square root of -1. Double y is equal to pow of 0 to the 0. And double z, what was the other one I was thinking of? 1 divided by 0. There we go. All right. And let's print all of those out. X, y, and z. X, y, and z. A variety of things will happen. Oops. Oh, first of all, it's complaining already that, wait a second, you can't do that. You can't divide by 0. I'm smart enough to realize that you can't do that. Well, you're not smart enough if I can trick you. 0.0. And I'll change that into a b there, right? And now it won't be able to detect that, right? It's giving me another error, but for a different reason there. I'll tell you what to do here in a second. -lm, there we go. We'll cover that here in a second. But let's actually go ahead and run this now. So square root of -1 should be I. Pow of 0 to 0, undefined or something. And 1 divided by 0 should be, if you're put it on your calcat for a second, maybe infinity, right? Negative not a number, 1, and inf, right? So lots of different weird stuff happens. Why is it like this?
Anything to the 0 power.
Yeah, anything to the 0 power, that one rule, right? Except for what about 0? 0, that would mean that you can get something out of nothing, and that doesn't make any sense either, right? So that's less interesting, but what is this nan? Not a number, right? So this results in nan, which is not a number. Well, of course we know that it's a number. It's an imaginary number. That's a terrible name. It's actually a complex number, right? It's not imaginary. It's just complex, right? And this is inf or infinity, right? And this is 1 for some reason. Reasons, maybe, right? So that's just what they decided that it should be. Probably there's some specification out there that says if that happens, it should be like this for reasons, right? But otherwise, weird stuff can happen. Just do correct math, right? Don't try to divide by 0. Don't try to do complex numbers, et cetera, et cetera. Something like log of 0 would be negative infinity. You can have positive and negative values there. So do be careful on that. All right? There are other math functions that are going to be, here's the other gotcha, right? Sometimes when you use the math library, you have to help the compiler, there we go, find out where it is. Right? So for example, compile using gcc foo.c or demo.c or mymath.c, whatever your program is, -lm. The -lm is going to, lm means link in the math library, right? So I'll highlight those. L, link in the M math library. Right? That's what it's referring to. The reason for this is some 40 years ago, they thought, well, wait a second, everybody's going to want to do math differently, right? And the standard math library, they're going to do it one way, but other people might want to do it another way, so they kind of separated that library out into a different library. Note that we don't call it STD Math, we just call it math, because it is a standard library now, but at the time, they thought, well, there are going to be other standard math libraries out there. Maybe they don't want to use our math library, and we don't want conflicts for our version of square root versus your version of square root. And there are dozens and dozens of different algorithms that you can use to compute the square root. Right? Which one do we use? We don't care. But as a burden to us, because of that decision way back 40 years, sometimes you have to use the -lm flag here to link in the math library to get it to work. If you don't do that, you'll get an error message that looked like that. Undefined reference to square root. Why? Oh, well, that's in the math library. What do I need to do? I need to make sure that I link in the math library, and then it'll be okay. Right? So, those are some pitfalls of basic operations. All right? Any questions so far? Yeah, go ahead.
So why did they think other people were going to develop a bunch of other standard math libraries if
There's a great C FAQ, -lm, why? You could read all about it there. I don't know if it's going to come up here. I guess I should say C programming. I'm getting a bunch of weird other stuff. There, CFAQ, frequently asked questions, -lm, find math. All right, it's somewhere in there. You're going to have to dig deep for it. I'm sure that they've got their reasons, and they're probably not very good ones, right? Same reason that, why did we call it SQRT? It's because they were saving on space 40, 50 years ago that no longer matters, but because it's like that, we're still stuck with it. Right? Yeah?
Is there also a limitation to how big your scope can be?
How big your what?
Your scope can be?
Global is your limitation. I could create I shouldn't even show you this because you should never do this. In fact, there's an idiom, globals are evil. Right? You should not use global variables. But let's go ahead and show you what it looks like. Evil variable, there we go, is equal to 42. Right? There, every single line of code now that gets compiled with this program sees evil variable right there. Every single line of code knows about it. Every single line of code can change it. So you have to test for the eventuality that every single line of code will change it. And now you're in chaos land because there's no predictability. Right? It's much harder to test programs that use global variables like this. But otherwise, generally, if you declare it inside of these curly brackets, then it only exists inside these curly brackets. If I can put arbitrary curly brackets wherever I want, there we go. There's a new scope. It's an inner scope. Now, X, Y, and Z only exist up until line 18. So if I tried to compile this again and try to print them on lines 20 through 22, it ain't going to know about them because they died on line 18. Right? They were born on line 15 through 17, and then they died on line 18. And they're no longer in scope. Right? Literally, you can see this as scope because use your curly brackets on your submarine scope or something like that, and you can only see that section right there. So let me go ahead and get rid of that. Oh, remind me, how can I fix that indentation really quick and easy? A style of demo. All right, there we go. And close it, open it again, or reload it. Hey, it fixed it for me. All right. A style is, I forget what the A stands for, but it'll stylize your code. Just get in the habit of writing good styled code already. Okay? All right. Well, what about this input and output that we've been doing up to this point? All right. Formatted output. Let's go back to the notes over here. There we go. All right. So let's talk about input, output. Because that's actually the programs that you're going to be starting on here for next week, especially next week's lab. You're basically doing a basic input output. You're going to be reading some input and giving it output, computing a result, and then putting in output. So the printf can be used to print formatted data, right? So note there that I am highlighting the words that count, print and f. That's why it's called printf, right? You can change the default, by default, there are several placeholders that you can use in a format string, right? For example, if you want to print out a floating point number, you would use %f. Formats, I should say, formats a double. Right? The defaults to 6 decimals of accuracy. Right? So let's go back up here. Let's play around with pi, m sub pi again. So pi is equal to this. I'll go ahead and get rid of all of this here since we've done it. There we go. So GCC-LM A.out. There we go. 3.141593. How many digits of accuracy do you see there? To the right of the decimal place. I see 6, just like I said. Right? That's the default. Right? We're going to talk about how to get to change that default here in a moment. But to print an integer, unfortunately, it's not I. That would make sense. It's D for digit. D for digit. Right? Prints on int. Right? D should have been for doubles, right? But it ain't that way, right? The only one of these 3 that makes sense of the 3 variables that we've looked at so far is %c. Formats a char variable, right? You can provide as many placeholders in a string as you want, but the order matters. Let's go back to our original miles to kilometer program over here, right? %f miles is equal to %f kilometers. Miles is going to be associated with that first placeholder. KMS is going to be associated with that second placeholder. If I switch those around, of course I would be getting the wrong data. Let's go ahead and actually test this out. I don't think I've changed anything substantial. There we go. A.out. By the way, you don't need math library for the basic arithmetic. Right? A math library is for advanced math, like square roots and sines and stuff, right? So let's go ahead and run this interactive program now. So miles, yeah, 3.11 miles. So that's significant because I'll use this as an opportunity to plug the first Wednesday of every month. There's a 5K run with the School of Computing. So if you're interested in running with us, a couple of the faculty members and as many students as want, very few ever actually show up. But if you want to, you can show up next Wednesday at 3:30 outside the Shore Center, and we'll go around campus at a 5K. Because we're doing it in the afternoon and it's still kind of hot, it's going to be 86, so dress appropriately and bring your sunscreen if you're coming. Right? But otherwise, you can come out and run a 3.11 mile with us, which is how many K? Roughly 5K. Right? So 3.11 miles is equal to 5K. Right? Again, if I change these, I would not get the correct amount. KMS miles. Let's do that again. Right? Please enter miles, 3.11. All right, and I'm getting the wrong 5 miles is 3 kilometers. That's definitely wrong. Right? So let's undo that, undo. And also, if you have 2 placeholders, but only 1 variable, it's going to warn you about that. Warning, this expects a matching double argument, but you only gave me 1 variable over here. So it will try to save you from yourself, but that's just a warning. This will actually run and give you some results. I don't know, 10 miles. 10 miles is going to be 10 kilometers? One for one? Definitely not. It's going to give you garbage results because of that. But make sure that you're doing it correctly, and it'll actually work. 16 kilometers, right? So you can provide as many placeholders, but the order matters. You can change the default. You can change the default formatting using modifiers. Right? So the general form, you can do this with any of the others, like integers and characters, but it's only really useful for floating point numbers. So %f is your usual placeholder, but you can actually put two numbers before that, x dot y, right? And here are some examples. Here's the examples. And let's just do this in code over here, right? And I'm going to do it in the demo. The default is to print 6 decimals of accuracy. What if you want more decimals of accuracy? What if you want, say, 10 decimals of accuracy? You would be putting in 0.10f. Right? What if you only wanted, say, 2 decimals of accuracy? Let's do just 2 decimals of accuracy and then 10 decimals of accuracy. GCC demo.c, and run that. And you see that I've got that many decimals of accuracy, only 2 decimals of accuracy, and then I've got even more decimals of accuracy. Let's do this for 4, though. Let's add one more. Just 4. There we go. All right. Is pi 3.1416? No. 9, so what do you think happened here? It rounded up for the purposes of printing. That did not change pi. Right? We see that pi is unchanged down here. It's still the accurate pi that we all love and know. But it has changed up here for the purposes of printing. Right? That's one number. You can also do the other number. So let's take all of these over here and put them down here. You can put another number over here. Let's just go ahead and go 10, 10, and 10. What this first number is a minimum number of columns. Okay? I'm going to print a minimum number of 10 columns. Well, if pi is only going out to 2 decimals of accuracy, that's going to be 3.14. How many decimals, or how many spaces are left over? How many columns are left over? 6. So let's go ahead and run this and see what it does instead. 1, 2, 3, 4, 5, 6. It pads it out with a bunch of spaces. Here we're printing a minimum of 10 columns, but 3.1416, I count that as 6 columns already. So how many columns out front that are going to be spaces? 4. What about over here? I wanted a minimum of 10, but 10, that's a minimum. So it's actually going to print out 10 decimals of accuracy, plus the period, plus 3. We've already exceeded 10. So it's not going to put any space in front of this at all. That extra space right there is from me typing it right there. Why would you ever want to do this? Well, think about a typical ledger, right? If you're printing a bunch of figures, all the periods line up, right? So that it's easily readable. And you can use printf functions like this. And yes, you can use them for integers. Int x is equal to 1,234. Printf %, what was the placeholder again for an integer? D, right? And the line, x. But I want to modify this so that it's at least 10 digits. I count 1, 2, 3, 4 digits there. So how many in front? 6, right? Why would you ever want to do this with integers? Well, does anybody's NUID starts with 0? At least 10% of you should. So among 80, there should like be 8 of you out there, but just by chance. And I see like 4 hands now. And so you can pad it out instead of spaces, you can pad it out with zeros. So maybe somebody's NUID is 0001234. We can go ahead and get that kind of formatting like that, except that NUIDs are what? 8 digits? 8 numbers, right? There we go. There's your NUID printed correctly if you have leading zeros. Printf is almost a universal. Every programming language is going to support printf style formatting. There are dozens and dozens of other placeholders and dozens of other tricks that you can do like this to print it in binary, to print it in hexadecimal, to do a whole bunch of things in different formatting. But that's basically the tip of the iceberg and all that we're going to cover. I'll see you on Wednesday because there is no class due to Labor Day, on Monday.